We know that as we've gone through, most of the reactions that we've looked at have been exothermic. So most of the reactions that we've looked at, most reactions are exothermic. And that makes sense to us. We kind of figure, yeah, reactions are going to be exothermic because when we draw the enthalpy profile diagrams, which we've been doing since GCSE in many ways, if we plot enthalpy along that, and then we've got reaction coordinate going on there, we would say let's do the burning of methane. Methane CH4 as a gas plus 2O2 as a gas. Exothermic reaction to give me CO2 gas plus 2H2O as a liquid. The reason I put it as a liquid is I'm going to say this is under standard conditions, which is at 25 degrees C. No, it's not. Yes, it is. So that means water is going to be a liquid. Delta H is going to be a negative figure. It's exothermic. So what is that telling me? That's telling me that the bonds in the products are stronger than the bonds in the reactants. They've released energy, energy's been released into the surroundings, and I've lost chemical energy. So chemical energy that was stored here, my chemical energy is gone. So these bonds are stronger than those bonds. So it makes sense that that reaction happened because I've got stronger chemical bonds. So why on earth do any endothermic reactions occur? Because based on that, endothermic reactions shouldn't be possible. All reactions should be exothermic to make stronger chemical bonds. So, endothermic reactions, however, why do endothermic reactions happen? So, what would be an endothermic reaction profile? Well, let's just do a quick one here. We would have reaction coordinate going along there. And going up here we'll do our enthalpy as well. This time, let's do the thermal decomposition of magnesium carbonate. Magnesium carbonate is going to go up to give me magnesium oxide as a solid plus CO2 gas. And delta H in this case is going to be positive. Typical endothermic reaction, but this is suggesting to me that my bonds in magnesium carbonate are stronger than my bonds in magnesium oxide and carbon dioxide gas. But this is a reaction that will happen. That will go, but why? That one we're happy with, but why on earth does that happen? This, in order to sort of like explain why endothermic reaction, why all reactions happen, is we have to consider this term entropy. So we have to always consider two things: enthalpy, which is energy, and there's another thing called entropy. Entropy is a measure of disorder. Now, the key thing is the universe wants to become more and more disordered as it goes through its lifetime. So that's the key aim. For a reaction to happen, the overall entropy of the universe, which we'll look at later, must increase. We must be getting more and more disordered. So, entropy, what on earth does that mean? Well, entropy simply measures, now you can get into the physics of this, but we're not going to worry too much, measures how disordered a system is, or something is. So at the moment, you guys are way too ordered. You're all sat down in rows. The universe does not like you for many reasons, that being one of them. So you were way too... Okay. If you were bouncing off the walls, flying around, the universe would be much happier because you'd be more disordered. You would be all kind of going crazy. So, entropy measured how disordered it is. Now, it's very logical. Now, if you think about it, well, a lot of the things you have to do is compare compare the entropy of a solid, a liquid, and a gas. What do we reckon? If I compare the solid, a solid is going to have quite a low entropy, isn't it? Everything's ordered, everything is in a fixed position. Liquid, slightly higher entropy, slightly more disordered, and a gas, a far greater disorder. In order to make this sort of make sense, we're going to put some figures up so that you can see what these actually mean. So this is called the second law of thermodynamics. The second law of thermodynamics basically say a spontaneous reaction which is a bit of a weird term, but we're sorry, must result in an increase in the entropy of the universe. And you may kind of think, oh, why is he talking about the universe? I'll explain it. So it must result in an increase in the entropy of the universe. And that's known as the second law of thermodynamics. What do I mean by spontaneous reaction? A spontaneous reaction is simply one that will naturally go.
Like aluminium forming aluminium dioxide?
Yeah. Is one that once started will go naturally. So sometimes I need to start it. So for example, the methane, which we looked at earlier, I need to give a spark to it to get it to go, but once I've sparked it, it's all going to go up. So a spontaneous one is one that once started will go naturally. In order to decide, and that's what your questions will always be on, will this reaction happen? You need to consider two things. You need to consider the reaction, but also you need to consider what's happening in the surroundings. So you need to consider the rest of the universe as well. So we need to consider the entropy change of both the reaction and the surroundings. To decide whether it will happen.
Is that more or less important than entropy?
That's a very good point. Basically the same. You need to consider both. So we have to look at the enthalpy, which the enthalpy is actually telling me about what's happening in the surroundings. The entropy is looking at the specific reaction and number of particles involved, which we'll look at. But you have to consider both. When we'll look at how they're weighted a bit later on.